In this lab, we are studying Newton's second law by applying it to the motion of an object with constant velocity. I have rolled a weighted medicine ball across a flat surface, and the net force acting on the ball is equal to 0. I observe that the ball rolls at a constant velocity across the surface. My objective is to understand and predict the motion by using Newton's second law to create a model for the motion and to see how accurate the computational model created is. I then compared the computational model motion to the experimental motion and found that the model predicts that the ball rolls slower than I found in my experiment, for reasons that will be discussed later, but for the most part, the computational model creates a good model for the real-life motion of an object moving at constant velocity. My experiment setup consists of the ball sitting on the origin of my chosen coordinate system and rolling in the negative x direction, with the x-axis in the horizontal direction and the y-axis in the vertical direction. The calibration stick has been set to 1 meter, and the meter stick used to measure this is set in the background of my model. As we can see in the tracker model, the ball rolls at what appears to be a constant velocity, as shown by a straight downward sloping line since the motion is in the negative x direction. If we were to flip the axes so that the x-axis becomes the y-axis, so that now the ball is rolling in the negative y direction, the data in the columns of the data table would flip, since the motion is now in the y direction. However, the magnitudes of the velocity would remain the same since the ball is still rolling at the same velocity, only in different directions. Since we now have our experimental data collected, we move on to our computational model. The most important part of our model is Newton's second law in the update velocity form, as shown here. This will go into our code as part of our loop. However, since Fnet is equal to 0, we can prove that the final velocity is equal to the initial velocity, meaning that the velocity will be constant, and this proof is shown here. This leads us into the update position equation, which is also an important part of our code. Since we have proven that the initial velocity will always equal the final velocity, meaning we have constant velocity, we know that the average velocity is equal to the initial velocity, and the code will run the loop for us as the delta t increases. Thus, the code is updating the velocity and the position and creating a model for the motion based off of the initial position and velocity from the tracker data. To complete the code, I have gotten the initial position from the tracker data using the first data point, and I have calculated the initial velocity here using data from tracker. I have also updated the mass and time of observation in the code. Moving to our computational model, when we run it, we see that our computational model exhibits motion similar to the motion we observed in the model, rolling to the left, which is the negative x direction, at a constant velocity. Now that we have collected both our model and experimental data, we move on to comparing the two sets of data. After collecting all the data into one spreadsheet and setting the model and the experimental data side by side with the times, I have created this graph, which represents the two motions. We can see that the two are very similar at the beginning, but as time goes on, the two begin to drift apart, with the model predicting that the ball wouldn't have traveled as far as it did in the experiment. The reason I found for the discrepancy is that the ball was actually accelerating. I calculated the velocities for each time interval, and the velocity begins to increase in the experimental model, eventually increasing from negative 0.97 in the first time interval to negative 1.06 in the final. This means that the ball is not actually rolling at a constant velocity and is actually accelerating. This is attributed to the fact that my flat surface might not have been as perfectly flat as I thought it was. It is impossible to determine the exact pushes and pulls based off the data collected because we can only measure net forces, not the individual forces acting on an object. We also know that at zero net force, the forces acting in the horizontal direction must cancel out as well as the components in the vertical direction. However, we cannot be sure how many forces are acting, so we cannot determine the magnitudes of the forces, we just know that they must cancel out.